All right, class, we are ready for section 5.3, which is all about talking about and comparing the linear functions that we really discussed in chapter 2 for the midterm. That's what the midterm was over and everything, right? And the exponential functions that we've started discussing in chapter 5. So we have these two functions that we can generate to represent a scenario, and we want to be able to now compare these two tools that we have to represent scenarios. Okay, so the first thing we want to do though is realize that so far we can come up with exponential functions in almost every scenario. We can come up with linear functions, except for we haven't talked about how to create exponential functions given any 2 points. So far we've only talked about how to create that exponential function when we're given that initial value or C value. So what we want to look at today and what we're going to start with here is to come up with an exponential function given any 2 points. You'll notice here we don't have that C value because again the C value is the y-intercept, just like it's the B value in linear functions, and we don't have that point where x is 0 and we would have the C for an exponential function. So we need to learn how to do this. We need to learn, okay, what do we do when we don't have that initial value that we're given? So we're still working with an exponential function. So we still have y equals c times a to the x. But at this point, we have neither c or a. We don't know the growth factor and we don't know that initial value. So what do? Well, we do have a couple pairs of x and y's, right? But that would only get us this x and y here, and we'd still be left with not knowing c or a. So what we do is we say, all right, well, let's just treat the lower x value point. So in this case, 2 is smaller than 5. So treat the lower x value point as the initial value. So step 1 is essentially going to be to kind of rig this so we can use it. So use 212 as the initial value. Okay, so what does this mean? We're going to use that as the initial value, so then we can use 5, 4, and use 5, 4 as that point we can plug in for x and y. Okay, so here's what happens. This 4 then is our y value, this 5 is our x value, and the initial value is always the y value. So we're going to use c equal to 12 as that initial value. But what's going to happen then is it's going to affect how we plug in the x value, because we're going to assume then that x starts at 2 rather than 0 and then goes to 5. So it's kind of like reinitializing x when we do that with years, right? We say years since 1980, and then 0 becomes 1980, right? We're reinitializing x so that an x of 2 is where we're starting. So what that means is as I'm plugging this in, I see that y is 4 from my point. That's going to equal my initial value, c of 12. I don't know a, so that's what this step is going to help me find is a, the growth factor. But this exponent is where I'm left with a question mark, right? What do I plug in? If x is 5, I don't actually plug in x is 5, because that would mean actually 7, right? 5 steps after my initial value of 2. So here you'll always take the x value from your point and subtract away that initial x value in order to get something that is reinitialized, to treat that 212 as the initial value. And I'm seeing here that my screen is not updating with what I'm writing. So I'm going to pause here for a second and see if I can't get it to update here. Okay, looks like it's working, so we'll see how this holds up. Okay, so see, we took the 5 here minus the 2. All right. Oops. There we go, 5 minus 2. All right, so we've reinitialized x, treating 212 as the initial point, and now we can solve for a because it's the only variable we have in this equation. So let's continue to solve for a. This becomes 4 equals 12 times a cubed. Then we'll need to divide both sides by 12. Simplifying there, 4 divided by 12 will be 1/3 equals a cubed, and then just remember to undo a power, you can take the root. So we'll take the cube root, or the power of 1/3 of both sides. Okay, so that will cancel the power on a, and that will tell us that a equals whatever 3 to the 1/3 power is. Now, sorry, not 3, 1/3 to the 1/3 power is. Now we can find out what that is and find the growth factor, but remember, we have a lot of error if we round in our growth factor. So this is where I'm going to say, okay, start to leave this as is. Don't actually simplify that. That's a number to a power, and we're going to use a in that exact form, the last exact form we have before we would have to round a in order to solve this. Okay, so we have a now here. So then we move on to step 2, which is going to be to find the c value. So just to kind of catch up real quick, right? We're starting with y equals c times a to the x. So far, we know that y now, we have the a value. We don't have the c value, right? For step 1, we kind of jimmy-rigged the c value to be something where we could find a. So now we're going to find c, and we see here that a is 1/3 to the 1/3 power, and then a is taken to the x, right? So we can simplify this. Our power to power rule says we can take 1/3 times x. So right now our function looks like y equals c times 1/3 to the x/3 power. Okay, so now we're going to use this function to do step 2 to find the actual c value. Okay, so step 2 now is going to be to use either point. It doesn't matter if you use 2/12 or 5/4, use either of your original points to find the c value. So you're going to use either of these points as an x and a y and find the c. Okay, so let's do that. I'm going to go ahead and use 2/12. You could use 5/4, and because we don't have that rounded a value, we'll get the same answer either way. All right, so I'm going to use 12 as y, c is what I'm looking for. That's times 1/3 to the 2/3 power then, because x is 2 and y is 12 if I'm using that first point. Okay, so again, don't do any rounding as you go. It's okay to round c at the end, right? Because it's a number we only multiply by once. Whereas we never really want to round a if we don't have to, because it's something we multiply by over and over and over again because it has that exponent. So here we are going to have to do a little rounding with c at the end, but that's all right. So we're going to divide both sides by 1/3 to the 2/3 power. We're going to find that in our calculator and then divide by it. Okay, and make sure you grab your calculator and you can do this. When you take that, you'll end up with just c left over, and c will be about 24.961. Now I'm still going to keep about 3 decimals there to try and keep as much accuracy as possible. But again, it's okay to go ahead and round c because we're not multiplying by it several times. So our final equation then is y equals 24.961 times a, which is 1/3, and we're going to leave that as the fraction in the power, so we're not rounding at all, to the x/3. And we found the exponential function between any 2 points, and really that extra step now is to do that, treating one of the points that's not an initial value as an initial value to find a from the beginning. Okay, so don't worry, we're going to do that again. But if you got confused, this is a video, right? So go ahead and start it over and watch that again and see if it doesn't help. Because what we're going to do next is do this in context. Okay, so what we're going to do next is say, okay, where's a scenario where I might have 2 points, a scenario in context, right, where I might have 2 points and I need to find the exponential function. So we've realized that accounts, right, that are have a certain interest rate have exponential growth, and so that's what we're going to look at here. But this time we're not given that interest rate. What we know from this particular example is that after 2 years, we have a bank account balance of $65,000. 4 years later, they make $4,420 in interest. Okay, so we also have to do a little work here to come up with those 2 points, but there are 2 points hidden in this information. So always when you have context, set up your variables first. So we know we're working with bank accounts, so we're going to have this exponential growth, y equals c times a to the x. In this case, years are passing and my balance is changing. So x is going to be years and y is going to be the balance of the account. Now it's important that you realize that it's the balance of the account. So the first sentence gives a pretty easy point to use. We see that after 2 years, we have $65,000 in the account. Now the second point is a little bit harder because it says 4 years later. After 2 years, we have $65,000. Then 4 years after that, so the next point that we want to look at says, okay, 2 years have passed, 4 years after that, so that's 6 years into this account being left alone to collect interest. Then what's our balance? Because our y is our balance. So after the 2 years, we had $65,000, and in these next 4 years, we gained $4,420 in interest. So the point we want to use is that after 6 years, we have $69,420. So we have 2 points, and we want to find the exponential function between them. So see if you can't pause this and come up with that function by following the steps from the first example there. But we're going to go ahead and do this, okay? So remember, step 1 is to always use that lower x value. So in this case, the 2, we're going to use that 265,000, point as the initial. Okay, so that means we're thinking about years since that first 2 years. So see if you can get that set up into the equation correctly then. So that means that over here, our other point at 69,400 is going to be our x and y, but we always want to pay attention to x and make sure we reinitialize that so that 2 is the initial x value. So y can go in just like we see it. So y is 69,420. That equals the initial amount 65,000, which gets multiplied by the growth factor, which is what we're always trying to find in the first step here. And a is always taken to x minus that initial x. So here we're going to end up with 4 for a power there. Okay, so 6 minus 2 becomes 4. Okay, now to solve for a, you should have divided by 65,000. And so this is going to be, so plug that into your calculator and see if you can't get something that's at least nice looking. If not, then we're going to leave that as a fraction because we don't want to do any rounding along the way. And that does work out nicely. That's a terminating decimal. That's 1.068. So we can go ahead and leave that. I would go ahead and do the decimal because it's not a rounded decimal. It has just as much accuracy as this confusing fraction up here, okay? Then we need to take each side to the 4th root or 1/4 power. And that's when we leave the 1/4 power. We don't actually take it, so we don't round. Okay, so a, what we're going to use for a is 1.068 to the 1/4 power. Okay, so think about what your equation looks like now, right? As we move on to do step 2. This was a different problem up there. Okay, so as we move on to do step 2, we've got right now y equals, we don't know c because we were just using a makeshift c in step 1. We do know a now though, 1.068, which is to the 1/4 power, and that gets taken to the x, so it's the x/4 power. We've done no rounding at this point, and that's really good because we're finding a. We don't want to round as we find a, or we're going to see some mistakes. Okay, Step 2, remember, is to plug in either point. So you can plug in either point here. And by either point, I mean you can plug in either of those originals. So you can plug in that 265,000 or the 669,420 point, either one. I'm going to plug in the first one. It's smaller numbers, might be a little easier to work with. Okay, so I'm going to pick this one. You might have picked the other one. So my X is going to be 2 and my Y is going to be 65,000. So 65,000 equals, C is what I'm looking for, 1.068 to the 2/4 power. Okay, C is where we can do some rounding. So we're going to divide off by whatever 1.068 to the 2/4 or 1/2 power is. We're going to do that to 65,000 and we're going to get a number. Now again, keep as much accuracy as you can, but C would be an initial value. So we're going to maybe round it to the nearest cent because that would make sense for money. Okay, so that's what I'm going to do. And we get here that C then equals $62,896.68. So that would have had to have been our initial investment or what we had at whatever year 0 means for this account in order for the other 2 points to have worked out. So put it all together at the end, Y equals that C value 62,896.68 times that non-rounded growth factor 1.068 to the x/4 power. Okay, and that would be your final function for that scenario. So again, go back. If you didn't get it, try and find your error. Go back and watch that again if you're stuck. This can be a little bit tricky for sure at first. Okay, so now that we have the tools to find an exponential function in any scenario, we can also find a linear function. We can start comparing a linear function in a scenario to an exponential function and how those two would be different going through any 2 points. So we just want to do a little recap here. A linear function, remember that form is y equals mx plus b. We know how to find linear functions back from chapter 2. And now we know how to find exponential functions in all the same scenarios that y equals c times a to the x. All right, so what we want to do now here is, okay, if we have a set of data now, we can determine, okay, is this data linear or is it exponential? What type of function matches this data? Now, of course, data can be neither linear or exponential, but we have a couple of different things to check now, not just checking if it's linear, but checking if it's either linear or exponential. This is also a good review back from chapter 2, and I would always start with linear because that's just easier, right? The function itself is more simple than an exponential function. So let's check first to see if this data is linear. You guys remember what you do to check that? You should find and see if the slope is consistent, right? If that rate of change is consistent. So we're going to first start by finding the rate of change between the first 2 points there. So find the change in y, 10 minus 16 2/3 over 3 minus 0. Grab your calculator to help you out with that. You'll get negative 6 2/3 in your numerator over 3 in your denominator, and that will give you a slope of negative 20/9 when it's simplified. Always use the simplified fraction because you want to make sure you don't have a rounding error and end up saying it's linear when it's not. Okay? Once you do the first 2 points, move on to the second 2 and see if that slope is consistent. Here then we'd have 6 minus 10 over 6 minus 3. That's negative 4 over 3. And right there we can see that this is not linear because the slopes are not equal. We have to have a constant rate of change, and that's not a constant rate of change already, so it's not linear. So then we would move on to say, okay, is this data exponential? And there's not really a quicker way than just coming up with the function and seeing if it works for the rest of the points. That's kind of my favorite way to test if something is exponential. Okay, so what we do have here though is a little bit of a break because we have that x equals 0 point. So we can see right away that if we're talking about an exponential function, that our c value is going to be 16 2/3. So this will be a little bit easier to come up with the function. So that's what we're going to do first. We're going to come up with the exponential function between the first 2 points and then test the next two to see if they follow the exponential function defined by the first two. Okay, so we know c has to be 16 2/3. So what we're going to do is use an x value of 3 and a y value of 10 to come up with the a value. All right, so plugging in that x and y, we have 10 equals 16 2/3 for c. Whoops, that doesn't look like a power, but it is. 16 2/3 for c times a to the x, which is 3. Okay, again, from using that point, the second point in our table. All right, so then we can solve for a. We'll divide each side by 16 2/3. Sorry, that's not a power. That is just a number. I don't know what I was saying before. 16 2/3 is just a number. That's not a power. So divide each side by 16 2/3. Getting all confused here. Okay, dividing both sides by that 16 2/3. In your calculator, you should get just another fraction there. That's 3/5 when you do that division, equals a to the third. And so then we will take each side to the 1/3 power, and I do mean power there, to take that cube root of both sides. Okay, again, leave this a as is. So then your function would be y equals 16 2/3, not 16 to the 2/3 power. 16 2/3 times 3/5 is our base of a, and our power is 1/3 of a, so that would be to the power of x over 3 for the function. So this would be the exponential function between the first 2 points. Now we are going to test the next 2 points. So we're going to test x equals 6 and see if we get out y equals 6. So then that would be 16 2/3 to the times 3/5 to the 6 over 3. And if you plug that into your calculator, you do get an output of 6. So that point works. Then you're going to test the last point there where x equals 9 and see if you get out 3.6. So plug in 16 2/3 times 3/5 to the 9 over 3 in your calculator, and you will in fact get out 3.6. All right. So because all the points work for that function, not only do we know it's exponential, but we actually know the function right now. And can you tell me at this point, is it exponential growth or exponential decay? And you can do more than just look at the factor, right? Because we always want to be careful with the factor, because right now the factor isn't by itself. So we would need to take 3/5 to the 1/3 power to see if that factor was between 0 and 1 or greater than 1. Other thing you can do is just realize that your y's are going down. So this has to be exponential decay. And done. Okay, so there is some work to that, right? I'm not trying to say that there's not, but it's repeating the same steps. So we're just getting a lot of good practice on how to generate these exponential functions and thus tell if data is exponentially related or not. Okay, so we're going to do this again, but that function up top worked out really well. And actually I had to do some work to make sure that it worked out really well, because a lot of the time with exponential function outputs, right, we're not going to get nice rounded numbers, nice, clear, easy numbers. So what we're going to have to do here is be a little bit more careful as we're testing and realize that these output values that we're given here are rounded values themselves. So we want to make sure that we're taking that into account and not looking for the numbers to match up exactly as we're testing, let's say, in our exponential function, but that we're as close as we can be. So if we're really close, then we're still going to say that this is an exponential function. Or if the slopes are really close to consistent, we're going to say that it's linear because we know we're working with rounded numbers from the beginning. So start off there by testing those slopes and seeing if they're constant. Okay, so the first thing you should do is take 12.95, test these first 2 points. 12.95 minus 9.17, change in y over change in x, 3 minus -1. Plug that into your calculator. I'm going to plug it into mine, and we're going to see if this is linear. We get a slope there of 0.945. So we're going to see if the next slope between the next 2 points, 3 and 5, is constant with that. So 15.39 minus 12.95 over 5 minus 3. All right, take that in your calculator, see what you get. And there we get 1.22. Those are nowhere near equal, so that is not linear. Okay, if they were off by maybe like 100th or 1,000th, then I would go ahead and test the next point because we know we're working with rounded numbers. But those are off by a lot more. There's no way that's the same slope and that this is linear data. Okay, so now let's check to see if it's exponentially related. Now we are going to have a little bit more work here, right? Because we don't have, unfortunately, an x value of 0 to work with. So we're going to have to pick 2 points to work with, find the function, and test the other points. Now you do not have to use the first 2 points, and in fact I wouldn't, because it's going to be a little bit hard to think about reinitializing at x equals -1. So you can use any 2 points to generate an exponential function. So I'm going to go ahead and just move out of the negative x's so I don't have to think about what it looks like to reinitialize from a negative x. And just go ahead and find the function between 3, 12.95 and 5, 15.39. Okay, so let's do that first. So we're going to find the function between 3, 12.95 and 5, 15.39. Okay, so you know how to do that now. Pause, see if you can find that same function. Don't round along the way for a, okay, if you can help it. So step 1, we're going to reinitialize. We're going to say, okay, this is x and y. This is going to be c, and we're reinitializing at an x value of 3. So then we have that 15.39 equals our c value, 12.95 times a to the 5, but always subtract off that initial value of x, which is 3. So divide both sides by 12.95. And then when you do that, if you take 15.39 divided by 12.95, you're going to see that that's not a nice decimal. So I would leave that. Okay, it's not going to be necessarily pretty, but I would leave it so you're not rounding along the way and creating even more error, possibility for error as we go. So that's going to be that fraction equals a squared, and we would square root both sides, or if we want to think about it so the power makes more sense, we're going to take both sides to the 1/2 power. And I would leave that a just as is. Okay, so now what we have is that y equals, whoops, see if I can get that to look more like an actual equal sign there. There we go. Y equals, c is what we don't actually know now. We do know a. A is that kind of crazy fraction, right? It is 15.39 over 12.95 to the 1/2 power, so x over 2 for the function. The less you round, the more you're going to be sure that it is in fact exponentially related or not at the end. Now we need to find c, so we can use either of these original first 2 points to find c. I'm going to go ahead and use the point 3, 12.95, but you could use 5, 15.39. Okay, so I'm going to move on to step 2 here. I'm going to plug in x is 3 and y is 12.95. So 12.95 equals, C is what I'm looking for, times 15.39 over 12.95 to the 3 over 2. And you guys are just going to start to get real comfortable with your calculators here, right? So divide both sides by this entire term. So we're going to divide both sides by 15.39 over 12.95 to the 3/2 power. Okay, that's going to cancel that on this side, and I'm going to get an answer over here. Now this is an answer I can round because it's my C value. So take a second, pause if you need to. I'm going to go ahead and plug that into my calculator as well. So when I plug it in, I'm plugging in 12.95 divided by, open up a parentheses for the entire denominator, then open up another parenthesis for the fraction, 5.39 divided by 12.95. Close the one parenthesis, raise that, open a parenthesis, 3 divided by 2, close that parenthesis. Then close the final parenthesis for the end of the fraction. Sorry, the end of the denominator. Okay, you should get then a C value equal to 9.9958 about. And if you did round earlier, check and see how did that affect your C value in the end, right? Okay, so be careful with that. So your final function then is y equals about 9.9958 times 15, whoops, I always want to put that decimal place too soon with 15 for some reason. 15.39 over 12.95 to the power of x over 2. Now, I'm not saying that this is easy, guys, but just don't get too overwhelmed by all the numbers. The steps are the same. Just keep those numbers as you go. It just basically means you have more to plug into your calculator. So remember, this was the function. Let's go back to our table. This was the function between these 2 points. So now we need to test x equals -1 and x equals 10 and see if we get the same answers there. Okay, so x equals -1, plug it into your function. Okay, what do you get out for an output? So there, when you type that in to your calculator, you should plug in 9.9958, open a parenthesis, 15.39 divided by 12.95, close the parenthesis, hit the power key, open a parenthesis, type in -1 divided by 2, close the parenthesis, and get a value out. I end up, if I round that to the nearest hundredth, I get exactly 9.17, and that's why it's so important to keep as much accuracy as possible throughout, because there I got it to match up exactly, okay? If you didn't keep as much accuracy throughout, you might have gotten something a couple hundredths off, and that's what I'm saying. Don't be discouraged by that. Don't think, okay, it's definitely not an exponential function if you're only a couple hundredths off and you know there is rounding from the beginning. So do that again. We also need to test the last point, because if the last point doesn't work, none of it works. This one was good. These we used to build the function. So now we need to plug in 10 and see if we get out about 23.67. So I plug in 10, and notice 10 is going to multiply by this factor a lot more times, right? But we didn't round in the factor, so we should be pretty accurate here still. If you round it in this growth factor, this is where you're probably going to see you get off a little bit from the answer in the table. Okay, so if you plug that in again like we did with the other one, but plug in -10 for your x instead of -1, make sure you get all those parentheses in there like we did last time, then you should get, oh sorry, not -10, but +10. Hopefully, I actually did plug in -10 when I plugged it in my calculator, and I was like, oh, this isn't exponential. But if you plug in +10, you will get out, and I still got something a little bit off. I still got 23.70 when I rounded. But the further out you go in x, the more error you're gonna see. So this is okay to be off a little bit. We're still gonna say that this is exponential, and it's gonna be exponential growth because that function, right, we can see that just in the outputs here, the function is increasing as x increases. So this is exponential growth. Okay? Again, These are good to see a couple times. So if you need to go back, it's a video, go back and see that again. All right, we have one more to do here, and I think you're gonna like this one, but give it a shot. Always test to see if it's linear first, right? Because we see how much work exponential is. So let's rule out if this data is linear first or not. So testing those first 2 points, I'll take 6.5 minus -1 over 3 minus -2. And that will give me a slope of 1.5. If I continue on to the next 2 points, I'll take 8 minus 6.5 over 4 minus 3, and that will again give me 1.5. So I gotta check the last one though. It's looking pretty good though. Looks like it might be linear and we might get a little break here. And if you take that last one, 12.5 minus 8 over 7 minus 4, you get 1.5 again. So because this is constant, we do have a linear function. If we have a linear function, there's no way it's exponential, so we don't need to test for that. This is a linear function and it's growing in the output as x grows, so this is linear growth. All right, so take a breath. We did it. All right, lots of good examples there, so hopefully that'll help you with your homework. I do want to do one more actual comparing linear versus exponential. This is a really good example of when we would want to compare those two functions, come up with those functions and compare linear growth to exponential growth in a scenario, and maybe get an interesting conclusion here, because we know how fast exponential growth is, right? So if we don't want something to grow fast, we would think that we would want linear growth instead. And I say we would think that we would want, so you're probably just saying here, okay, something interesting is probably going to come out here, where maybe somehow exponential growth isn't as fast as linear growth in some scenarios. And how would that be possible? That's why we want to look at comparing exponential versus linear. Sometimes things are a little bit interesting here. So if you need to, pause, take a break, okay? We're going to continue on with this example here. So what we've got is that a local university is looking to increase its parking fee. So a good example of when, as a student paying for parking, I wouldn't want this to go up very fast, right? What we know is that it currently costs $3 to park on campus per day. They've put up 2 proposals about how they should increase this amount over time. Proposal A is to gradually increase the fee by 5% each year. And proposal B is to make a 20-cent increase each year. So we have a difference here. Increasing by a percentage, just like accounts increase by a percentage, is exponential growth. Increasing by a constant amount of 20 cents each year, right? If you continually add 20 cents every year, that's a constant rate of change, and we have linear. So proposal A is going to be exponential and proposal B is going to be linear. And we're going to see why and how here as we think about what's going to happen over a few years. So if this is exponential and this is linear, we would maybe expect this one originally to grow faster, right? Because it's exponential growth, it's growing by a percent. Let's see what happens. So in both times, we're going to start out with a fee of $3, right? That's what it is right now. So let's test it out, proposal A. So we need to increase this $3 by 5%. So if we think about just focusing in on this proposal A, we're going to take that $3, we're going to keep the $3 and add 5%, which is 0.05. We're going to take 3 times 1.05, and you should get $3.15 will be the amount it costs to park after 1 year with a 5% increase. Then after 2 years, we're again going to take this previous amount and multiply it by 1.05, or take the original amount times 1.05 for 2 years, right? Seeing that exponential growth. When you do that, you'll get that after 2 years, they'll charge $3.31 for parking. After 3 years, increasing it by 5% for 3 years straight, students will pay $3.48 to park. And after 4 years, we'll take that 3 times 1.05 to the 4th power, and students will pay $3.65. So let's compare that to a 20-cent increase, which is a little bit easier to calculate, right? We don't even need a calculator. After 1 year, 20 cents later, we'll be paying $3.20. 20 cents later, we'll be paying $3.40, then $3.60, and then $3.80. And notice that this linear growth, we're going to pay more after the first year with linear growth, right? Exponential growth is greater than linear growth. Exponential growth is great. Sorry, I'm doing this the wrong way. Exponential growth is not greater, right? Linear growth is greater. Linear growth is greater. Linear growth is greater. All the way through for 4 years, it actually turns out that that linear growth, that constant amount growth is more, right? It's basically saying that 5% of $3 is not 20 cents, right? At first it was only 15 cents, then 16 cents increase. So it's increasing by more each year, but still not matching up to the second proposal. So let's generate those functions to see what happens, because we know that proposal A is exponential, and we know that exponential growth will always take over linear growth eventually. But what we're seeing right now is that at first, it's not. And we're going to visualize that here at the end to see why. Why is that happening? Okay, so that first proposal, can you generate a function for the first proposal to model the cost of parking after X years? For proposal A, you should get the following function. Proposal A, we get y equals the $3 times the growth factor. It's growing by 5% every year. For proposal B, we get that constant rate of change of 20 cents for every year, with that initial value being 3. Okay, another good test of creating those exponential and linear functions. So now we can quickly use those functions instead of having to do every year, right? We can quickly use those functions to figure out, okay, can we figure out when this exponential growth will finally take over the linear growth and grow faster, like we are pretty sure it should, but we're starting to kind of question maybe right now? So take that proposal A and plug in x equals 10. Then plug in x equals 15. So for proposal A, we'll take $3 times 1.05 10 times. And we'll get that after 10 years, if we continued with this proposal after 10 years, the cost to park will be $4.89 a day. After 15 years, we'll take it times 1.05, then 15 times, and we'll see that it'll cost $6.23 after 15 years. So do that for B as well. So this time we'll take and add 20 cents 10 times to $3, and we'll get out $5. So we'll see even after 10 years, the exponential function is still less than the linear function. Let's see what happens after 15 years. Y equals 0.2 times 15 plus $3. And for the first time we see that's $6, and for the first time we see the exponential function takes over. And we know that exponential growth eventually takes off. So let's see the visual. If you graph both of these functions up here, I did that on the last page of these notes. This is what we're visualizing right here. So the linear growth is this line right here, right? It's growing constantly forever. The exponential, oops, and I just highlighted the wrong line, of course. The linear growth was higher, right? So the linear growth is the one right here. And eventually it switches, right? So we've got proposal A right here and proposal B right here. We saw that after 15 years, so right around, let's see, was it after 15 years? After 15 years, right, they had switched. This is then proposal A, and this is proposal B. Remember, at 10 years, we still had B above A. So we can see that they do intersect eventually. Looks like around a little after 12 years, maybe around like 13 years, they would be equal and switch. But before that, what's happening is that linear growth, that exponential growth is lower, kind of zooming in on that change, and then eventually it's going to take off, right? Eventually this part is going to take off, and we're going to see a really big difference between linear and exponential. So if this policy is going to stay in place for, let's say, around 20, 25 years, then certainly, even though at the beginning the linear function is going to be higher, we're going to see that we want to go with that linear function because the gap isn't very big here, but it's going to get really big out here. But more than likely, this policy about parking isn't going to last more than a couple, 3 years. So if that's the case, we actually do want to go with the exponential growth if we only know it's going to last for a short amount of time. And we actually have quite a bit of room here, right? 12 years before reevaluating a policy, probably not going to happen. We're probably going to reevaluate that. So we would really actually go with the exponential growth there at the beginning. Because exponential growth can be a little bit slower growth, at least at the very beginning, than depending on the slope of that linear function, than that linear function. Okay? So some interesting stuff there. At least I think so. Hopefully you guys think so as well. You're going to be comparing a bunch of different scenarios of linear and exponential in your homework. So reach out if you have any questions, and I'll be happy to help you guys.